In the active region only, the BJT acts like amplifier. Okay. In the saturation region and in the cutoff region, the BJT is working like switch. Okay. So the switching operations are because of this. We are using the saturation and cutoff in the switching operations. Okay. So in the saturation, see, during saturation current IC is very high. I'll talk about VCE, it will be 0 and practically it's 0.2 for silicon type of BJT. Okay. Now what is the cutoff? In the cutoff, IB will be 0. So IC will be 0. Everything will be 0 in this region. Okay. So cutoff means RCE is infinity. The resistance between emitter and collector become very high. So this is the cutoff region. If resistance is very high over here, means these two terminals of BJT are open circuit, so there will be 0 current. Is it okay? So last time we have seen one problem in which we identify how to find out which region in which the BJT is working. Today also I'll take one problem and then we'll start the session. Okay. So the question is given over here. I'll draw in 15 seconds. This is 3K, 5 volt, emitter, grounded, okay, fine. This is 100K, and this is 2.7. Is it okay? Beta for this circuit is given 100 and they are asking find out this V0. This is the question. Now how you will proceed, you know? You will proceed this question like, wait a minute, let me change the color. Yes, VBE is always given and that is 0.7. If not given, then you have to consider it. Okay. This is the current IB over here in the circuit. This is the input circuit. This is output circuit. This is output and this is input. Okay. So in the input, I can apply the KVL over here, right? I'll start with 2.7. So it is 2.7 minus 100K into IB. Why I'm taking minus? Because the drop in the 100K is like this. Okay. And I'm getting 0.7 over here and to ground. So this is all about 0. 2.7 minus 0.7, it will be 2 equal to 100K of IB. Is it okay? Sorry, I'm sorry. So IB is 2 divided by 100 milli. So this is nothing but 20 milliampere if I am right. Okay. So this is IB and IB you calculated 20, this is micro. 20 microampere. Okay. Okay. It's perfectly fine. So once you calculated the IB, then you will calculate IC and IC is beta IB. If you remember this formula, so beta is 100 into 20 micro. So your answer is, this will become 2 milliampere. Once IC is 2 milliampere, what you will do, the IC is over here in this circuit and that is 2 milliampere. So here I'll having drop and drop will be equal to 3K into 2 milli. So that is equal to 2 milli and 6 volt. This is the drop over here. And they are saying that find out the V0. Now you have this circuit over here, you have 5 volt. This is grounded. Okay. You have to start your journey from this point. You have to reach to V0. So you can get V0 and your V0 will be, you will start your journey from this point. So you'll get plus 5 first, then you will get minus 6 in this circuit, and at the output you will get minus V0 equal to 0. So your V0 equal to minus 1 volt. In 4 option, this answer will be available there. You will tick it, and you will tick this number 1. Suppose you are having 4 options. Out of 4 options, at position 1 you are having V0 equal to minus 1 volt. Immediately you will mark it. At the same time you will lose your 0.33 marks. Okay, and 1 marks question itself. So total you are losing 1.33 marks. This is absolutely incorrect. It is not correct. Why? Because any circuit in the examination, please note it down. If any circuit given in the exam, first check the transistor in which region it's working, whether it's active or it's saturation. So you have to first check these 2 things, then only you have to proceed. Okay, so please note it down. This is the procedure for any circuit, BJT circuit. If they not mention its active region or saturation region, you have to find active region or saturation region, then you proceed. Okay, so what is the fault I am telling you now? Let me draw it again. The question given is, I am drawing it again. Within 15 seconds I'll draw it. This is grounded, 100K, and this is 2.7. Yes, obviously we are having 0.7 drop over here. So this is all about 3K, beta is equal to 100. Now the question is same. Find out V0. Okay. So in the last video lecture, we discussed about the steps. How to find out the region of operation. How to find region of operation. Right? In the last video lecture itself, we discussed about this. So we had there the first step, and that is find IC saturation first. You have to find IC saturation. Secondly, you have to find IC active. IC active. If IC active, in the third case, if IC active was greater than IC saturation, so this condition is not possible because IC saturation is the max current in BJT. So in this condition, when IC active is greater than the IC saturation, your diode or your transistor will work in saturation region. But if IC saturation is greater than IC active, your diode is in active region only. Is it okay? So we'll apply these steps into this circuit, so it will be clear to you. Okay? Fine. How to find out IC saturation? To find IC saturation, you need to short these 2 points. Collector and ammeter, you have to short it. Once it's shorted, you can find out IC. And now in this case, this IC is IC saturation. So IC saturation, when you will apply the KVL in the circuit, will be 5 divided by 3K. So this is 5 by 3 milliampere. So your IC saturation is 1.66 milliampere. This is your IC saturation. Correct? Okay, fine. When you apply the input, KVL in the input, you will get IB. And we have done this part. We got there, it was 20 microampere. Now we multiplied this by beta. So we got IC there. IC is beta IB. So here we are getting, this is 2 milliampere. So this is your IC active. When you will apply your circuit or your KVL into the input and you are finding IC, that current is the active current. If you are finding the current by applying KVL in the output circuit or output loop, you are getting IC saturation by keeping obviously VCE equal to 0. So here see, IC active is greater than IC saturation. IC active is greater than IC saturation. So your BJT or your transistor is working in saturation region. Saturation region means the voltage here and here is 0. Now they're asking what is V0. So V0 is now directly connected to ground, so it will be 0 volt. So the option will be 0 volt. If you don't have 0 volt, then you'll be having 0.2 volt in the options. They will give options like 6 volt, 2 volt, 1 volt, 0.2 volt. So you have to mark this. Is it okay? So this is the procedure and steps how to find out the region of operation. I hope this is clear to you. Let's come to the next topic. Wait a minute. Now we'll discuss about the current little bit. We already discussed about the diode, right? And diode characteristics. Diode is working in forward bias if you are connecting the positive terminal of the battery to the P type of diode, and or instead of P type I should say it anode, and this is the cathode, right? So if you'll connect the positive terminal of the battery to cathode terminal, the diode will be in reverse bias. Okay, so this is the diode symbol, and if I'll talk about the transistor symbol, so this is the transistor symbol, right, where this is emitter, this is collector, and what about this? This is the base region. Okay, so we have the current equation for these two elements. Let me take the pen first. So for this, if the current is ID, so this current ID nearly equal to ISE into e to the power Vd by eta Vt. Okay, where ISE is the saturation current, or I can say this is the reverse saturation current, not saturation exactly. This is the reverse saturation current in diode. Okay, when the reverse saturation current will flow in the diode, when you will connect into the reverse bias, in the reverse bias there will be no current in the circuit, but due to minority carrier and temperature effect, you are getting some very minute current over there, that is the reverse saturation current. So ID in the diode will be I reverse saturation multiply with e to the power Vd by eta Vt, where Vd is the voltage across diode. Okay, eta is 1 for germanium and eta is 2 for silicon. Okay, and Vt at room temperature is 25 millivolt. Okay, this is the temperature equivalent voltage. Okay, so 25 millivolt. So this is the equation for diode circuit. But if we'll talk about the transistor circuit, so here the current is IC, and your IC will be I saturation multiply with e to the power VBE divided by Vt, where VB is this one. Okay, this is looking like you are applying the input to the transistor, and this is like output. So your output is equal to Is e to the power VBE by Vt ampere. Please remember this. Okay, where what is the Is? Again, this is the reverse saturation current. Okay, this current will flow when the both junctions are in reverse bias. Okay, one ICO will flow in the circuit due to minority carriers. Okay, I think you heard about this into the electronics device and circuit, or in the detailed study of transistor. Okay, so I'll not go deep into this. You have to remember the Is is the reverse saturation current. We'll see FET circuit also. The symbol of the FET, later we'll know about this, is given like this. Over here I'll be having ID. So the ID in FET is given by ISS 1 minus VGS by VP whole square. Okay, we are having 3 elements. These are the 3 elements we are going to discuss. We discussed already the diode. Now we are discussing the transistor part, and later we'll see the FET, right? 1 minute. So in the diode, the current is given by ID equal to IAC to the power VD divided by eta VT. If we'll come into the transistor, the current is IS to the power VB by VT. And if we'll talk about the FET, it is ISS 1 minus VGS by VP whole square. Is it okay? So let's come to the next topic now. Reason of operation is clear to you people. So this is the equivalent circuit of transistor. Okay, let me take pen first. NPN transistor. I told you earlier the emitter current will come out from NPN. Okay, because see, in the NPN, we have seen the NPN, it was like this was the NPN, no? Right? So we are applying this junction with forward bias. Okay, forward bias means just like this, and to this junction I'm doing reverse bias. I'm doing like this something, right? So see, from this circuit the electrons will go like this. From positive to negative the current will come. So definitely your I will be outside from the transistor. So here in this case this current is outgoing current. So in the case of NPN transistor, your current will be outgoing current, and IE will be equal to definitely IC plus IB in any case. So this is the symbol. You can check over here also. From the emitter the current is coming out. Okay, and is it okay? See, if we'll talk about the PNP transistor, the current is coming into the, so actually this equivalent circuit is not that much important, but we are just seeing like this. We can represent it in the NPN, the current will be outside. In the PNP the current will be going into the circuit. So based on that we have drawn this too. Now we'll come to the biasing, and before biasing let me tell you one thing. It's related to the amplification. Okay friends, suppose you have the output characteristics of some device. Let's take it BJT itself, or let's take diode. This is the current in diode, this is the VD across diode. Okay, now you are applying some input and you are getting some output. But if you need some amplification kind of thing, see here I'm taking this thing. Though this is the output, I'm taking this one is the working region, operating region. Okay, in this region only I'll get the output, and this is the region where I'll apply the input kind of thing. Okay, so in this case suppose I applied input over here like this. Okay, so this input just have to plot in output by this relation. Okay, so the input portion is coming from CE. From every point I can draw some lines like this, like this, like this. So this is the input mapping. Suppose this is the input mapping. So equivalent this much thing, it will be output. So this is output mapping. See, this output mapping is just, equivalent to input mapping. Okay, or related to the input mapping. So in this case only distortion part of the output will come. This much part will come like this. It will come like this. So whatever you applied at the input, at the output, it's completely distorted. Right? If you are applying the input at t equal to 0. So you are getting like this. So what we have to do, if you want to get the full output, you have to set first the region of operation, and that should be linear enough. Let me erase it and again I'll tell you. This is the system characteristics. Now you have to choose this option, this one, right? But now you are not applying time at t equal to 0. You have to do some shifting in your waveform. So your waveform will come to this position. This is the input mapping. Right? This is input mapping. So your input will come to this position. Like you shifted your input. Let's take your input you are applying over here. So how this is possible? How you can shift your input? By adding some DC part. Is it okay? In the clamper circuit we have seen this. In the clamping means shifting means we can add some DC part. So we can change the position of whatever voltage or input you have. So corresponding to this input map, the output map is like this. This is the output map. So if this full part is covering the input and the output also I'm getting the full lines, means full mapping. The output mapping is completely equal to the input mapping in this case. What is the case? First you should choose the linear region like this, and second you have to add some DC part so you can shift your input. Why we are shifting the input? So now if you'll get the output, your output will be complete replica of input. Okay? There will be no loss in this condition. If you have chosen this point appropriately, the proper point you have to choose. This point we call the operating point. Later we'll discuss about it. But this is kind of, we are adding some DC part into the small signal or AC signal. So we can shift the level. If we can shift the level, the signal come to this linear region, and once the signal input is in linear region, the input output mapping are equivalent to or equal to the each other. Is it okay? Now wait a minute. Let me tell you one thing. Let me erase it first. See, this is the DC and AC, and here we'll take elements, right? First element we'll discuss about is resistors. The resistor in DC is like this only. In the AC, same, there is no problem with resistor in any DC or AC. No problem at all. In the second case, we are choosing inductor. Okay. So inductor for DC, earlier we discussed it. DC has zero frequency. Over zero frequency, the inductor acts like short circuit. And for AC, it will act like inductor. Sorry, this is not inductor, this is inductor. Okay, for the AC circuit, it will provide its value. For DC circuit, it will be short circuit. If I'll talk about the capacitor circuit, now come to the capacitor. For the DC, capacitor acts like open circuit. Okay, if you remember this. And for AC, it will working like this, capacitor itself. Now we have introduced diode also. So we'll consider diode also. Okay. For the DC, diode will act like this. One battery. Barrier potential battery 0.7. If you'll apply a DC input to the diode, you will be having the equivalent circuit is 0.7 voltage drop. Okay, shown like this. If you're applying DC to the diode, diode will act like this. What if you'll apply AC to the diode? If you'll apply AC to diode, diode will, diode will work like resistor. I can take this RD, D for diode, and this RD is given by VT divided by ICDC. Okay, this is the temperature equivalent voltage. At room temperature, the value of this is 25 millivolt. So 25 millivolt you have to divide with ICDC. ICDC means you have to apply DC into the diode, then you have to find IDC. That current you will divide 25 millivolts you will divide by that current, so you will get the RD. So this is very important, very important concept. Okay, please remember it always for the AC. Okay, sorry, for the AC circuit, diode acts like resistor. Is it okay? So let me take one example based on this. Friends, the question given is, this is 1K. Here I have 4 diodes connected in this way. In series they are connected. Okay. I have input 2 sin T in millivolt in series with DC 5 volt. So for this circuit, the question is, find total current. Find total current into the circuit. Okay, this is the question. Now, if you observe this circuit, you have AC source as well as DC source, right? So what it means we have to apply the idea for DC and AC both. Why? Because we are having diodes in the circuit also. And we have seen just now, the diode works like simple drop across it for the DC source, and for the AC source, diode works like resistance, whose value is given by VT divided by IDC, right? IDDC. Is it okay? And VT for this question is given already 25 millivolt. Now they are asking find out the total current. Total current means what? Do you have 2 or more than 2 independent sources? Yes, you have. So can you apply superposition theorem in this case? Yes, we can apply superposition theorem. Means we can calculate the current one by one, and at the later stage we can add them. This is nothing but the superposition. So first I'll apply only DC part and I'll turn off the AC circuit or AC source. Okay, this is the AC source. Voltage is given, so we do short to voltage always. Means the voltage source will be short circuited always, as you know, right? This is the voltage source, so I'm just doing short to it. Is it okay? Instead of voltage source, if you have current source, you have to open it. Now in this entire circuit, you are having only DC part. If you are having DC part, you have to replace the diode circuits also, because we know for the DC part, diode works like a simple 0.7 drop battery, like this. So you have to replace all this 4 diodes. Okay, when you will replace them, so your circuit will be, this is 0.7, this is the polarity. Okay, because the P portion of the diode is given like this, anode is given like this. So this is 0.7 over here, again 0.7, again 0.7, and 4 times 0.7 actually. 0.7, 0.7, 0.7. Now if you will collect, if you will, get this current take is ID, and I'll call it DC, because you are having DC source into the circuit. So your IDDC is nothing but 5 minus 0.7 4 times. 4 into 0.7 divided by 1K. Is it okay? So this is 5 minus 2.8 divided by 1K. So this is kind of 2.2 milli. So 2.2 milli is your IC DC. Okay, so your DC is completed. You need total current. One part is over, that is DC current, and DC current you got 2.2 milli. So this part is over. So by superposition theorem, you consider the first source, that is the DC source, and you turn off the AC source, that is the second source, into the circuit. You calculated the output due to DC, or I can say you calculated current due to DC, and that current IDC you got 2.2 milliampere. So your first part is over. Now you will turn off the DC source and turn on the AC source. Okay, so situation will be completely changed over here now. Okay, let me take the AC source now. The AC source is given over here is, let me take, what was the value? The value was 2 sin t. It was 2 sin t. What I'll do with DC? I'll make it short circuit. Why I'm making it short circuit? Because this is the voltage source. What about these diodes? Now they are no longer working like 0.7 drop battery. They are working like resistance. They are behaving like resistance for AC, like this. This is RD1, RD2, RD3 and RD4. Okay, what is RD1? RD1 is nothing but VT divided by IC DC. DC current you already calculated. VT is 25 milli and this is 2.2 milli. So you have to divide 25 with 2.2. So it will be, if you will calculate, it will be 11.6 ohm. So you are having RD1 value 11.6. Similarly R2, R3 and R4 all will be having 11.6 ohm, 11.6 ohm, 11.6 ohm, 11.6 ohm. Now can you calculate IAC? Yes, I can calculate IAC. IAC for this circuit is 2 sin t. 2 sin t is the voltage, divided by 1K plus 4 times of 11.6. Is it? And this is given in millivolt. Okay, so this is millivolt. This is about IAC. Okay, you can calculate it by phasor method. This is nothing but given 2 at an angle minus 90. You have to divide by 1K plus 40, 45 and something like this. You can add and you will get some complex current IAC into the circuit. But they are asking the total current. For the total I total, you need to do is you have to add IDC part plus IAC part. As simple as that. Is it okay? So remember one thing, let me clear it. For AC, the diode is working like resistor RD, whose value RD is given by VT divided by IDC. Means if DC part is given into the circuit, first get the current IDC. For RD, which is working in AC circuit, RD is nothing but VT divided by IDC ohm. Okay, just replace the diode by RD in AC circuit. I hope the concept is clear to you. Now let's come to the next topic, and that is the biasing. Very important. Okay, what is the biasing? I think 5 to 10 minutes ago we discussed one thing. We draw the graph. This is the graph. Okay, now your task is to, you have to operate or you have to give your input to this region only, right? This is the 0 region, means you have to shift your input. So by shifting, it will come over here and input output mapping will match and you will get perfect output. Okay, so if you want to do this, first you have to apply some battery or not. Into the transistor you have to apply some energy source or not. So to apply some energy source, or I can say add some DC to the signal. This is fundamental thing. See, what you want is, you want to shift your input to this position. So you have to add some DC part, then only it will go up. Okay, it's not going directly over here. You can't consider over here. This is the graphical. But in actual, if you want to shift it, you have to add some DC part. We studied in Klemper circuits. So the purpose of biasing is add some DC part to the signal. Purpose of biasing is to switch on the BJT. You are applying some energy source, so definitely the BJT will be switched on. To work in active region such that the DC collector current is independent of the temperature. This is very important point written over here. Very, very important. The purpose in active region is to maintain the collector current constant. This is very important point. Later we'll illustrate this point. Okay, So purpose of biasing is to switch on the BJT to work in an active region. And why? I told you why active region is important, because in this active region only we are using BJT as an amplifier. The saturation and cutoff region, we are using those regions for switching applications only. I hope it's clear to you. So again, the purpose of biasing is to switch on the BJT to work in active region such that the DC collector current is independent of beta, okay, and temperature and load variations. Three things. We need to, this IC is function of this beta, temperature, it will affect due to temperature also, and load variation. But what we have to do, we have to keep it constant. So we need to, develop the device in such a way that the IC should not affected by beta, by temperature, by load variation. IC should be constant. Okay, then only amplification is possible. IC should not change. So in order for a transistor to amplify, it has to be properly biased. This means forward biasing the base emitter junction and reverse biasing collector base junction. Remember, we have to operate the transistor in active region. So I think it's clear to you. For active region, we need to do the base emitter junction, reverse bias. Wait a minute. In order for a transistor to amplify, it has to be properly biased. Okay. This point is correct. This means forward biasing the base emitter junction and reverse biasing collector base junction. Okay, we know about this. For linear amplification, the transistor should operate in active region. I told you, we discuss about this. We'll choose the linear region to work in. The transistor should work in this region only, so you'll be having better amplification. So in this region only you have to apply the input, that's why you have to shift it. So your input will come to this input mapping, right? So your input will be mapped at output same as input, okay? So for linear amplification, the transistor should operate in active region. If IE increases, IC increases, VCE decreases, okay? When IE will increase, when IB will decrease. Okay, or forget about this. See what they are saying. IE increases. We know that IC and IE both are nearly equal to each other. IE increases, IC will increase definitely. And when IC will increase, when VCE will decrease. Here is the VCE. When VCE is decreasing, it means IC increasing. Is it okay? At VC equal to 0 only, we are getting max current, that is the saturation. Okay. Now we are having various methods of biasing to the transistor circuits. Okay. So as we know, what is the importance of biasing? Biasing is used to, switch on the BJT. Okay, it's perfectly fine. But biasing should be there in such a way that your BJT is working like amplifier, or your BJT should work in active region. Your biasing should be in such a way that your transistor should work in active region, so you can use it as an amplifier, right? So that's why we are having various methods of biasing. Like this is the fixed bias or base bias. We are having potential divider also, common collector feedback, and so many biasing are here we have. So we'll discuss one by one. So we'll discuss this fixed bias in details. We'll see the DC load line, Q point and all about in this. Okay. So what is the fixed bias? This is your BJT circuit, transistor circuit. Okay. This is the base region, emitter region and collector region. Okay, perfectly fine. Okay. And we discuss about the, wait a minute, let me erase some part. The biasing should be in such a way that your IC should be constant. Okay, for better amplification we need constant IC. The collector current should be constant. This collector current is the function of beta, temperature and load variation. So what we have to do is we have to make this IC independent of beta, T and RCE. So this is another application of biasing or importance of biasing, right? So in this circuit the fixed bias is given over here and we have chosen NPN transistor, right? NPN. If current from the emitter junction is coming out, it means it's NPN. Sorry. This is N, this is P. Okay. So you applied battery over here in this way. This is the simple circuit. We are calling it the fixed bias. Because of this junction will be in forward bias. Because at P you are applying positive terminal, at N it is grounded. So this is forward bias junction. So the source VBB through a current limit resistor RB, this is RB, this is the current limiter. Okay, it will control the current, limit the current, how much current should go inside. Okay, RB forward biases the emitter diode, and VCC through resistor RC reverse bias the collector junction as shown in the figure. What about the collector junction? This is the N, this is P, so it will be definitely in reverse bias. This will be in reverse bias and this will be in forward bias. So the active region condition is satisfied. Your transistor will work now in the active region. Is there any problem with you? Why we are interested in only active region? Because the amplification is possible into the active region only. That's why. So the condition is fulfilled. The input terminal is forward biased and the output terminal is reverse biased. Let's come to the next now. The DC base current through RB is given by. Let me erase some part, then we'll discuss about this. This is the, let me take pen over here. So this is IB. Is it okay? Can you calculate IB for me? Yes, you can calculate easily. You will start with this. So your IB will be VBB minus VB. Definitely will be having VE over here, voltage drop. So this minus this divided by RB is nothing but your IB. I hope it's clear to you. So from this equation, only VBE is equal to VBB minus IBRB. VBB minus IBRB is nothing but VBE. Normally VB is taken 0.7 to 0.3. If exact voltage is required, then the input characteristic IB and VB, this is the input characteristics of the transistor, should be used to solve the above equation. Now the load line, see, the load line for the input circuit is drawn on the input characteristics. The 2 point of the load line can be obtained as given below. See friends, this is the load line, right? And this is the input characteristics. At the input you have, first of all, you have taken the NPN transistor. To this NPN transistor you have forward biased the input stage, you have reverse biased the output stage, forward bias. So this is diode, this is the diode characteristic, simple. VBE, you are applied to it and you are getting IB in it. Is it okay? So what is the load line? Load line we are drawing over here, and when the load line and the diode characteristics will cut to each other, this is the operating point. So this operating point we call the Q. Okay, the operating point means for the better amplification, your values of this different voltage and current should be this only, because we need over here, this is the reason, right? At DC, if you'll apply DC perfectly at this point only, you'll get the output. But when you apply AC, your input will fluctuate between these 2 points. So this is nothing but the Q point. So around Q point, if you are applying the AC input to the signal, it will fluctuate around Q. But if you are applying only DC part, so your output will be exactly at Q point. Is it okay? Let's come to the this point now. Wait. So IB is equal to 0, VB equal to VB. If according to this formula, if IB is equal to 0, means both are same. There is no potential difference, so no current. Okay. And for VB equal to 0, if you are taking VB equal to 0, IB equal to VBB by RB. So this is the load line between input current IB and output VB, input voltage VBE and input current IB. So if you will take IB equal to 0, you will get VBB equal to VBE. So you will take one value. For this entire line, the current is 0. When current is 0, the value should be VBB. Okay, I'm taking point VBB over this axis. At this axis, IB axis, VB equal to 0. At this line only, VB equal to 0. VBE equal to 0 at this line. So at this line, IB you are getting is VBB by RB. So you will connect these 2 points in this way. This is we call the load line. This load line is intersecting this. This is the characteristics at point. That point I call the IQ. So corresponding to Q, the value of VBE is called the VBEQ, and corresponding to Q, the value of current is called ICBQ. Okay, I hope it is clear to you, right? So the intersection of this line with input characteristics gives the operating point Q. See, we have seen over here, this is the operating point as shown in the figure. If an AC signal is connected to the base of the transistor, the variation in VBE is about Q point. This gives variation in IB and hence IC. Is it okay? Now we'll take, this is the input characteristics. Now we'll see the output characteristics of fixed bias. This is the fixed bias circuit. Simple circuit is given over here, and we are discussing about the load line. We are doing the load line for input and for output as well. Is it okay? So load line is the relation or drawn onto the relation between input voltage and input current. Now we'll see output current and output voltage. Is it okay? So now we'll see the output circuitry. Wait a minute. Now in the output circuit, the load equation can be written as VC equal to VCC minus ICRC. Let's come to the diagram over here. This is VC, am I right? If this is the current IC, this IC will be VCC minus VCE divided by RC. Is it okay to you? So the same thing is given over here. This equation involves two unknown VCE and IC. So definitely your load line will be in between or dependent on VCE and IC. Your output characteristics will take between VCE and IC and therefore cannot be solved. Okay. To solve this equation, output characteristics IC versus VCE is used. Now output characteristic is drawn between IC and VCE. So this is VCE and this is the IC. This is the variation. This all, see, these are the variation in IC with VCE. Is it okay? Now tell me one thing. When VCE is 0, when VCE is 0, in the diagram, if you remember, this is collector, this is emitter, and this is base. VC is 0 means short circuited. VC is 0. In this case, we were getting maximum current, that is IC saturation. So VC is 0 over here, or like here we are getting this is the saturation region. This region is the saturation region. Okay, and the max current in this region is nothing but the high saturation. Is it okay? Now let's come to the second thing, and the second thing is we are drawing the load line on the output characteristics, and the load line itself is drawn over VCE and IC. VCE and IC, this is the output of BJT. Output of BJT. If you'll talk about the input of BJT, the input characteristic is not important, but we were discussed about that. the input BJT relation will be in VBE and IB. This one is important, this is not. Because at the output stage we are checking the amplification only. So if you will draw the load line, how you will draw? When IC equal to 0, VC equal to VCC. So here I'll take it. This is the IC equal to 0, so this is VC, or I can say this is VCC. Why? This is the cutoff when current is 0 over here, right? Now, and VC equal to 0, if you will put VC equal to 0, you will get IC equal to VCC by, at this line only VC equal to 0, this vertical line. So at VC equal to 0, IC you are getting VCC by RC, you are connecting these 2 points. And this we call the Q point over here. Okay, whenever this transfer characteristics will cut the load line, we'll call it the Q point. Okay, so these are the different lines or different characteristics but different value of IBs. Is it okay? See, IB max is given at the max current of IB, the value of RC will be minimum, so the current will be maximum, IC. Is it okay? So the interaction of this line, which is also called the DC load line, and the characteristics gives the operating point Q as shown in the figure. So this Q point is nothing but operating point. Operating point says that this should be region in which the transistor should work for better amplification. So we need to choose this Q because it's in our hand now. VCC divided by RC is in our hand, RC is in our hand, VCC in our hand, and here VCC is in our hand. So we can control this Q. So we'll give the Q point or operating region, or we'll choose the operating region in such a way that the better amplification should occur in output. Is it okay? See, if your circuit you are taking like this, you will choose the Q point over here or over here or over here. If you'll choose Q point over here, you'll get distorted output. Input output mapping will not good over here. But if you'll take this point, so you'll get perfect input output mapping. So this Q point is in our hand, how we have to choosing it. Okay. Now one example is given, and the example says find the transistor current in the circuit. The transistor current we have to find if ICO is given 220 nanoampere and beta equal to 100. So friends, let me tell you about this ICO first. NPN. Is it okay? Now suppose you have done this reverse bias. This is the reverse bias. Okay. This is also reverse bias like this. Both junctions are reverse bias. In the reverse bias, will there any current in the circuit? IC will be 0. IE will be 0. The circuit is in cutoff. When both junctions will be in reverse bias, we have earlier studied about this, that this is the cutoff region. In the cutoff region, the VEB and I can say it junction EB and junction collector base, they are in reverse bias. In the reverse bias condition, we know there will be no current in the circuit, but still we are having some leakage current, this ICO, because of temperature. Because of temperature, the minority carriers are developing into the N region, and they will constitute current ICO. Is it okay? So this is the current. So the question is, find the transistor current in the circuit shown in the figure if ICO equal to 20 nano and beta is given over here. I have put the solution over here for you also. For the base current, see, if you apply over here, so it will be 5 and this is 0.7. So 5 minus 0.7 divided by 200k is equal to IB. So this is given over here. Okay. Now ICO is very less current. See, given in nanoampere. Nanoampere means 10 to the power minus 9, 0.00000000. It's very, very less current. Okay. So what is the question? So therefore ICO is less than IB. Definitely it will be, because IB is too high. It will be 4.3 divided by 200 milli equal to IB. So is it okay to you? So therefore IC is equal to beta IB. See, IC we have seen is beta IB. Is it okay? If this ICO is considerable, then formula will be beta plus 1 of ICO. This is the actual formula. The actual current IC will be beta IB plus beta plus 1 ICO. But though this current is negligible, so we are excluding this term. And simply we are taking, or we know already, the IC is nothing but beta IB. Okay, so we have to multiply beta. We got the IB current over here, so you are getting IC current. This is operating current, output current. From the collector circuit, VCE. Now we can calculate this VCE or not, tell me. VCE. We can calculate it. We can apply KVL over here. So it will be 10 minus 3K into the current. Current is already we calculated by this. So VCE we are getting 3.55 volt. Okay. Now VC is equal to VCB plus VBE. This VCE is nothing but VCB. Where is the CB? C. Here is the CB or not? This is base and this is VCB or BC. Let's take it BC. Is that okay? And this is between base and ammeter, VBE. So this is the circuit. So we are getting VC is equal to VCB plus VBE. So VCB is 2.55. So therefore collector junction is reverse biased and transistor is operating in the active region. Is it okay? So this is about this question. Okay. So we'll do this part in the third video lecture, and this was the theory part. Now we have to switch into the practice mode and problem mode. So from the next class onward, I'll come to this. We'll take problems, get problems. So the concept will be pretty clear to you. This is very lengthy unit, okay, because the theory part is more and more. So what I'm going to do over here is I have to choose problem part. So the concept will be clear to you people, right? Because from this question, they are not asking for theory part. They are asking simply questions, problems. You have to know about how to solve the circuit. So once I'll start the problems, you'll get automatically. Okay. So we'll meet in the next class. Till then, take care and bye.